a great honor and pleasure to have the chance to present here. So I would like to first thank the organizers to provide this opportunity for me and also my collaborator Lian. When Professor Yu asked me to consider a presentation in this talk, I was thinking like, what kind of my researches are mostly related to scalar curvature. I mean, it's a pity that I haven't had any essential works exactly on scalar curvature, but I feel maybe the mean curvature for hypersurfaces are sort of close analogs of scalar curvature for closed Riemann manifold. So I want to discuss some research related to the mean curvature, particularly constant mean curvature, hypersurfaces. I will focus more on sort of a little bit older results that happened in the past 5 to 3 years. Liam, my collaborator, will then present some more recent results. So this is the outline of the talk. I'll start with some old conjectures that's related to the talk. In the second part, I will quickly go through some results regarding the construction of MiMax constant mean curvature spheres. In the third part, I will talk about higher dimensional cases, constant mean curvature, or even prescribed mean curvature hypersurfaces. So actually, in the scalar curvature community, these prescribed mean curvature hypersurfaces are usually called the mu bubbles. At the end of the talk, I will discuss some of the applications of these constructions. I very much welcome any comments or discussions regarding the talk. I will try to explain some of the open problems. So it will be great if you can provide any of the insight or comments. Okay. So let me start with some conjectures raised by Arnold. It's about magnetic geodesics. So there were a series of conjectures. The earliest one I can find was a problem raised by Arnold in 1981, where he conjectured following, that every remaining two sphere, so this is a sphere endowed with a Riemann metric, I claim that there contains two distinct closed curves of constant geodesic curvature C for any positive number C. So in his original conjecture, he conjectured this for any closed surface with a Riemann metric, and there were some counterexamples on hyperbolic surfaces. So I think the open case now is mainly on S2. The conjecture is still open. I think it's even not known about the existence of one of them. So if you ask, say, the existence of one closed curve of constant geodesic curvature is also not fully solved. Later on, Arnold generalized his conjecture as follows. Let kappa be a smooth function defined on a two-sphere. He further conjectured, this was one of his conjectures. He has a few of them questions regarding this problem. So we can ask whether every remaining two-sphere contains two distinct closed curves of geodesic curvature prescribed by kappa. This part can be understood as follows. If I denote, say, K as the geodesic curvature of the curve, so gamma is a curve from S1 to S2. So prescribed curvature means that the geodesic curvature of the curve is given by the function kappa restricted to gamma. So that is called the prescribed curvature problem. Okay. One of the motivations that Arnold asks this type of problem is because such curves are the trajectories of a charged particle in a magnetic field given by the function times the area form. This is a two form, which will be automatically closed because it's a two manifold. So given a closed two form on a manifold, not necessarily two-dimensional, you can say this is the magnetic field. You want to ask, under this magnetic field, what are the trajectories of a charged particle? They must satisfy this type of ODE. And the conjecture can be viewed as the problem of finding closed trajectories. This is
May I ask you something? You said this counterexample for negative curvature. It looks slightly strange, yeah? It seems must be easier for negative curvature.
As far as I know, so there are hyperbolic surfaces. So where the CGC, constant geodesic curves, are the so-called horocycles. So they will never close up.
I see the up to level of horocycles, but everything below horocycles, of course, yeah. Any curvature is greater than horocycle, yeah. This is what you have.
I see. I say that this is there are counter examples for some C, but not for all of them.
Yeah. Okay. Yeah.
Thank you for the comment. So this is about closed curves of constant geodesic curvatures. There were also conjectures for surfaces with prescribed mean curvature. So there was a question raised by Yao in 1982 in his problem sections. It is more like an open question rather than a conjecture. He said that, can we find the appropriate conditions on a smooth function in R3 such that there exists a closed embedded surface with control genus and mean curvature prescribed by the function h? So this can be understood as follows. So if h is the mean curvature, so we want to solve the question that this equals the prescription of h restricted on the surface. So in the scalar curvature community, I noticed that this was first introduced by Professor Gromov. This is usually called mu bubbles. I think the motivation of Yao's conjecture was related to the partition of volume. Some question considered or asked by Almgren. A more recent conjecture regarding surfaces with prescribed mean curvature was the one raised by Rosenberg and Smith in 2010. This is a precise conjecture. They conjecture that every remaining three sphere, this is a topological three sphere endowed with a remaining metric. They say that every such sphere of positive curvature should admit an embedded two sphere of constant mean curvature C for every positive number C. This conjecture is very much analog of a three-dimensional Arnold conjecture. It's a special case because in the Arnold conjecture, there were no assumption on the curvatures. By the way, I want to say that if you assume that this is positive curve, I think this conjecture was already solved by Schneider, also around 2010, if the Gauss curvature is positive. Well, in this case, they just say that the curvature positive. They even didn't say precisely what positivity they want to ask. Also, the conjecture only asks for existence of one of them, not a pair of them. So these are some motivating conjectures, and I would like to start with some more concrete results regarding this conjecture. Before discussing the Rosenberg-Smith conjecture, I like to recall a result by Simon Smith in 1982. They proved that for every remaining three sphere, there always exists a close embedded minimal S2. So in this case, they find embedded S2 whose mean curvature is exactly 0. So this is a minimal surface case. They prove that using some like Almgren-Pease type MiMax construction. Now, if we compare this result and the Rosenberg-Smith conjecture, it seems that if you were able to generalize this for non-constant mean curvature, non-zero constant mean curvature, then you would be done. But unfortunately, it was shown by Torobo that for some particular number C, and for some particular Bourget spheres, all immersed CMC2 spheres of mean curvature C must have self-intersections. They cannot be embedded. So you can find immersed CMC2 spheres of this prescribed given mean curvature, but they must have self-intersections, which says that the original conjecture Rosenberg and Smith should be amended. A natural amendation that I propose is as follows, that we can amend this to say every remaining 3 sphere of positive curvature, we know that these Bourget spheres all have positive Ricci curvature, for instance. Every remaining 3 sphere positive curvature admits an immersed 2 sphere of constant mean curvature C for every positive C. So we just change the embedded assumption to immersed.
But are there any techniques to produce such immersed sphere? For embedded, you can calculate variations, but for immersed, is there any results when you prove?
I'm going to present a partial result admitting some branch points. Yeah, as a very good remark by Professor Gromov, the most effective way of constructing immersed surfaces, I mean, say CMC or even minimal surfaces, was to using variational idea, but to use the mapping methods. We use calculus variations, but we treated the image as a parameterization. So this idea was already pioneered by a list of works. They originally, I would say, if you talk about minimal surfaces, this was the classical plateau problem proved by Douglas and Rado. And for immersed CMC surfaces, this was pioneered by Hinz in 54, Hildebrand, Brizy-Coulomb, Strohl, and so on. What they were trying to do is to consider, say, a unit disk, and you look for a map into a convex body omega in R3. You want to solve so that the image has a plateau boundary, but the image has CMC constant mean curvature C. Following this idea, 2 years ago, Chen and I proved the following result, which we show that every remaining 3 sphere, a 3 sphere endowed with an arbitrary remainder metric with non-negative Ricci curvature, if G has non-negative Ricci curvature, we prove that such 3 sphere always admits a branch immersed 2 sphere of constant mean curvature C. Note that the theorem compared with the previous conjecture, the difference is that we need to allow some branch point. So here the branch point, I'm going to explain what does this mean in the next slide. Okay. So in this result, we assume the curvature, the metric has non-negative Ricci curvature, sort of coherent to what Rosenberg Smith asked. But for a general metric, we also have the following result. We prove that if you have a remaining 3 sphere with an arbitrary remainder metric, then we can show for almost all C, for almost all number C, there exists a branch immersed 2 sphere of constant mean curvature C. We cannot prove the problem for all C. We can prove this for generic set of prescribed curvature Cs. The major difference between the two results is that you can first prove this for almost all C, but if you use this almost all C to approximate an arbitrary C, the total area of the sequence of surfaces may blow up. We sort of use the Ricci curvature condition to control the area in some sense. Now let me explain a bit more of what we actually proved in the theorems. We actually try to solve a PDE for maps from a 2 sphere into an arbitrary 3 sphere, which was isometric embedded in some hair dimensional Riemann manifold. So now U is a vector value function defined on sphere whose image is constrained on some particular three sphere. So we were trying to solve this equation 1. The left-hand side is Laplacian of U. This is a vector value function. It's just a Euro-Laplacian. So this A is the second fundamental form of this isometric embedding. It's a vector value function on S3. It's a two form. So what we're plugging in is a grad U. So together, this will be a vector value function on S2. The right-hand side is, so we first take the isothermal coordinates on S2. So you can take the partial derivative. These are vectors in Rn, or these are tangent vectors in S3. And then we can take a wedge product in the tangent space of S3. Again, this is a vector in a tangent space of S3, or this can be treated as a vector in Rn. And we take the Horsch dual of the dx dy of this two form. It's a little bit complicated, but this tells us that the left-hand side is the mean curvature times this vector. Equation 1 tells us that the mean curvature of this mapping U is prescribed by the number C. You can also change C, for instance, if you want, you can change C to H of U if you want. Then that will give us a prescribed mean curvature of the mu bubble equation if you want. The theorems here mainly aims to solve a non-trivial solution for this PDE. As Professor Gromov just said, that we can try to use calculus variations, because equation 1 is the Euler-Lagrangian equation for this weighted Dirichlet energy functional. Okay. So this weighted Dirichlet energy functional consists of two parts. I'm going to give you more motivations in later slides using hypersurfaces and volumes. So let me be a little bit quicker here. The leading part is the Euler Dirichlet energy, just grad U squared integrated over S2. Now this weighted part is more or less the volume enclosed by U. Let me quickly plot a figure. So assume that this is S3, with arbitrary shape. Assume that this is the image of U. Well, U is allowed to be immersed or even having some singularities. This V of F measures the volume included by the blue curve. Well, unfortunately, in this case, the volume is not uniquely defined. You can have two different extensions which defines two enclosed volumes. But using degree theory, we actually know that for different extensions, the volume differed by integer multiple of the total volume of the ambient space. In short, we work on a weighted Dirichlet energy functional, which is multi-valued, but it's not too bad. It only differs by integer multiple or given number. So it's a multi-valued functional, but it's not that too bad. So essentially, we devise a calculus variation theory to show or to find a critical point associated with this weighted Dirichlet energy function. So for which the Euler-Lagrangian equation will solve this prescribed mean curvature type PDE. Yeah, maybe I used too much time for the first part. Let me just mention some quick remarks. My joint work with Chang can be viewed as a CMC analog of the famous Sachs-Uhlenbeck's results. We are forced to use a MiMax construction as the functional is neither bounded from below nor bounded from above. You see, that's because the enclosed volume can be negative if you extend to some negative oriented domain. So the functional is not bounded from below nor above. So we use MiMax. And also a classical challenge is that the energy functional does not satisfy any of the Pauli-Smith condition. So we have to use some regularizations, which we use for the biharmonic ones. So I just want to emphasize that we use Ricci non-negative condition together with the Morse index upper bound to show that any of the solution here, any of the solution for this equation have uniformly bounded area depending only on the number C. So the area bounds follows directly from Ricci curvature condition together with the Morse index bounds. So for that, we can solve for all C. So this is a quick outline of this result, which was not of my emphasis. So I just want to finish this part by raising some natural questions or conjecture. So Chen and I proved this result, allowing branch points that there always exists a constant mean curvature S2. So let's recall the question, say, conjecture of Yale of early conjecture Arnold. We can say whether can we find closed CMC surfaces with controlled genus and any given prescribed mean curvature in other closed three manifolds or three manifolds which are not S3. Direct corollary of my work with Chen is that, well, if the third homotopy group is non-trivial, you can still do the same thing. That's the same as what Sachs-Uhlenbeck did. If you have higher non-trivial homotopy groups, you can run a MiMax. Well, now I want to compare with the Simon-Smith theory I mentioned a few minutes ago. So in the original paper, Simon-Smith proved that every remaining three sphere contains a minimal S2. Their theory also works for arbitrary three manifolds. So you can prove the existence of a close embedded minimal surface of genus bounded by the Heegaard genus of the three manifold. So you can use a Heegaard splitting as a one parameter family to run the MiMax. So natural conjecture I would like to raise is that every three manifold admits a branch immersed CMC surfaces of any given curvature C and genus controlled by the Heegaard genus of the manifold. Unfortunately, my theory with Chen cannot solve this conjecture because we essentially use that the sphere has a unique conformal structure. And if you sweep out the manifold by higher genus surfaces, the conformal structure will be more complicated. And that's a little bit out of reach of our result. Okay.
Just one question, please.
Yes.
The boundness on the genus works properly to the variational methods, or is there a way to use it as a compactness result to ensure the existence of solution? I mean, how does the Heegaard genus appear there?
Sorry, I couldn't hear clearly. Can you repeat your question again?
Yeah, sorry. Is it better now?
Yeah.
Yeah, just one question is because the boundness on the genus works like some compactness assumption to use your variational methods, or does it appear in any other way?
So the result Chen and I work on, you can still work on this functional. You can find a solution to this PDE. But since the conformal structure is non-unique, if you work on a higher genus surface, the map may not necessarily be conformal. So the right-hand side is no longer the mean curvature.
I see. Now I see. Thank
you. Is that okay?
Yeah, great. Thank you.
Okay, so next I'd like to tell you another different story, which use geometric measure theory, and we can have more satisfying results. And I'll give you a comparison. So now I want to ask like a high-dimensional analogs of Arnold conjecture, or the Yale's conjecture, or Rosenberg-Smith conjecture. In this case, I consider a closed Riemann manifold of dimension n+1. So n+1 can be strictly greater than 3. Okay. So in this case, closed hypersurfaces of constant mean curvature are the natural analogs of closed constant geodesic curvature curves. In 2017, Jonathan Zhou and I proved the following theorem. We show that for every closed manifold of dimension between 3 and 7, for any positive number C, there always exists a smooth, closed, almost embedded hypersurface of constant mean curvature C. I will going to explain this. More or less, you show that if you just generally ask about the higher dimensional analog of Arnold's conjecture for one CMC hypersurfaces, the answer is yes. In this theorem, we again try to use calculus variations, but using geometric measure theory. So if the number c equal to 0, if you search for minimal hypersurfaces, this was due to Almgren, Pease, and Xin Zhou. And we try to generalize this to non-zero constant mean curvature hypersurfaces. So here the terminology almost embedded means that you can have several pieces of the surface, but essentially you can only have 2 pieces of the surface. They can touch each other, but not cross each other. This is sometimes called quasi. They call what they call the quasi Alexandro embedded. Also, well, a remark is that since we use geometric measure theory, we don't have a topological control over the solutions, even when the dimension is 3. I mean, as I said, in 3 manifold, you can consider the Heegaard splittings. If you run the theorem for Heegaard splitting, we cannot prove that the genus is bounded by the starting genus because we use geometric measure theory. So when you take a limit or when you run compactness, you can increase the genus. Later, I think this is 2019, they generalized our results to higher dimensions, allowing the solution to have a small singular site. Okay, so this is the CMC MiMax theory. So I think now I like to quickly talk about some quasi-Alexandrov. Okay, thanks for the comment. I like to quickly talk a little bit about the terminologies and see a geometric intuition behind how we ran through the calculus variations. So suppose sigma is a hypersurface inside the Riemann manifold. We have the following first variation formula, which says that if we deform this hypersurface by a vector field x and calculate how the area change up to the first order, that gives the mean curvature times the normal speed of this variation. So in some sense, the mean curvature is treated as the gradient of the area functional. And the simple fact is that if the hypersurface bounds a domain, say if the hypersurface bounds a domain, then it has constant mean curvature if and only if the first variation is 0 among all of the volume preserving variations of the domain, which means that the integration of the average of the speed is 0. But now I want to give you another perspective of treating this variational problem. So if you only look for surfaces which is stationary under volume preserving variations, you do get a constant mean curvature hypersurface, but you don't have a control of the mean curvature. If you want to have a control mean curvature, we should consider this type of weighted area functional, which I call AC functional. So the AC functional consists of the leading term, which is the area of the boundary, subtract a constant c times the volume of the set omega. So if this is omega, so the functional measures the area of the boundary, subtract this Lagrange multiplier term times the volume. So if we run the first variation argument for this functional, say if you let Vt to be a flow, then the first variation for the boundary area gives the mean curvature. The first variation of the volume term gives exactly the normal speed. So sorting them out, the first variation gives the mean curvature h, subtract this number c, times an arbitrary variation. So obviously this variation vanishes if and only if the mean curvature function is identically equal to the constant c. So to find CMC hypersurfaces with the prescribed number c, we have to look for this weighted area functional, or Lagrange multiplier version of the area functional. Well, our first thought is, can we minimize the functional to get a critical point? Well, unfortunately, on closed manifold, we cannot get a non-trivial solution by minimizations, because the total manifold, if you replace omega by the total manifold M, that's always a minimizer, because we can compare this with AC of M. So if I plug in this as a total manifold M, its boundary is empty. So only have this negative term. So ACM achieves the minimum of the functional over all subset of M. That's to say, if you take minimization for this functional, you get a total manifold whose boundary is empty. So you get a trivial CMC hypersurface. Okay. So for that reason, we have to consider the MiMax idea. So this is a sketch of the MiMax idea in multivariable calculus. In this picture, S is a piece of surface with a saddle point P. H is a height function. And we can represent the value HP as follows. We consider arbitrary so-called mountain path going from one part of the hill to the other part of the hill, and we measure the maximum. If we take the infimum over all such maximums, that should be achieved by the red curve. So HP, the value of a saddle point, is always written as the minimum over all one parameter passes of the maximums. So saddle values can be written as a MiMax. And if S is a closed finite dimensional manifold, we can use basic point set topology to show the existence of a critical point P, even if we don't know the expression of the function H. So the MiMax idea is similar, but instead we should work on an infinite dimensional space. I quickly plot an intuitive idea of Almgren piece and Xin Zhou. So in this picture, the surface represents an n+1 dimensional closed manifold. The blue curves represent a one parameter family of hypersurfaces that connect a point to another point. We call them a sweep out if the union of all the blue curves is exactly M. I mean, counting a cancellation of orientation also. So once we have the notation of sweep out, that plays the role of the blue curves. So we can mimic the definition and define a width. So that is, we take a sweep out, take the maximum area, and then take the infimum when the sweep outs change. Ideally, if each of the if of the hypersurface is an elastic rubber band, they try to shrink that area, but they still try to maintain as a whole. Ideally, eventually we have this optimal one parameter family represented by the red curves. And the maximum area one, ideally, would be a smooth minimal hypersurface. This is a very primitive idea of Almgren piece and Xin Zhou. And using that, they can show that the MiMax is always achieved by some closed hypersurface, which is smoothly embedded outside the codimension 7 singular site. Okay. So since every one parameter family should go across something that encloses half of the volume, using the isoperimetric inequality, it's easy to show that the base is strictly positive. So the number is achieved by some non-trivial minimal hypersurface. So the corollary is that every closed manifold admits a closed minimal hypersurface. Okay. So in my joint work with Jonathan Zhou, we try to generalize the idea of Almgren piece Xin Zhou to this weighted functional. So in this case, instead of considering one parameter family of hypersurfaces, we should consider one parameter family of subsites with finite parameters. So this is a set of Cacciapoli sites. So ideally, again, if this denotes n+1 dimensional manifold, we consider a one parameter family of subsites, so omega x. So such that omega 0 is empty and omega 1 is the total manifold. You start with empty sites, then you enlarge it so that eventually you cover the whole manifold. So for instance, if we give a Morse function, we can use the sub-level sites to construct such a one parameter family. Okay, I just mimic writing this one parameter family to define the MiMax. Due to a limit of time, how many do I still have?
10 minutes.
Okay, so sorry, just allow me to skip some more technical challenges. So again, we have to show that this MiMax is non-trivial. So we have to use some isoperimetric ideas for small volume sites. And then we want to show we can take some weak limit. So we have to define a generalized weak limit. And then we can run some so-called tightening process to show that in the first step, we get a non-trivial solution, which is stationary with respect to this AC functional. And after that, sorry, I'm a little bit short of time. I'm going to explore the almost minimizing concept of Almgren. This almost minimizing concept sort of tells you that your weak solution is locally approximated by some constrained almost minimizers. Essentially, there are some almost minimizers. So we change the almost minimizers by their corresponding minimizers. So in this step, we gain some regularity. The regularity we gain in the step is that this constraint minimizer is always smoothly almost embedded. So maybe I'll just point this part out. So suppose we have a sequence of CMC surfaces. Suppose that they're stable. Suppose they have curvature estimates. Then in the limit, even if in the sequence they are properly embedded, in the limit they can have some touching side. So this is sigma limit. This is a limiting process. This is a particular feature for CMC hypersurfaces, because if you flip the orientations, in limit, they cannot touch each other. They're still properly embedded. In this configuration, in the limit, they can be quasi-Alexandral immersed. Well, we essentially implored this particular feature. We can show that our solution, our CMC solution has multiplicity 1 due to the previous feature. Anyway, altogether, we show the existence of 1 closed CMC surfaces. Well, motivated by Arnold's conjecture, it's really tempting to conjecture that there exist 2 distinct closely embedded CMC hypersurfaces in every closed Riemann manifold. Well, indeed, so the mean curvature should run from, let me just say that in S2 or S3, let's see, this is a standard S3 with the round metric. So this is a north pole, this is a south pole. Well, if you start from here to look for all of these concentric spheres, if you fix the orientation, the mean curvature should go from -infinity to +infinity, right? So the spectrum of the constant mean curvature run from -infinity to +infinity. So my result with Zhou only solve this for, say, positive spectrum. Well, if you flip the orientation, you get the negative spectrum. But as compared with the standard example and Arnold's conjecture, it's really tempting to conjecture that every closed manifold admits at least 2 distinct closed CMC surfaces of any given positive curvature C. Okay, so that's something I call the twin bubble conjecture. Well, there were some partial results, but we don't have a definite result yet. There another interesting direction for this type of results is to consider non-compact manifold. So there were the results proved by Gromov and Song regarding minimal hypersurfaces in non-compact manifold. So I would like to just make a conjecture that if we consider an asymptotically flat manifold, this is manifold studied a lot in general relativity. I want to see for every number C, there should exist almost embedded hypersurface of constant mean curvature C. This hypersurface may not be closed. It can be non-compact with finite area. Okay. Another thing I want to quickly explain is that Zhou and I can also generalize at our CMC MiMax to find a general prescribing varying mean curvature problems, or generalized mu bubbles as named by Professor Gromov. We essentially show that for almost all smooth function on closed manifold, you can find a smooth closed hypersurface whose mean curvature is prescribed by this function h. Or in other words, for almost all prescribing function h, you can solve a non-trivial mu bubble in this dimension range. I mean, again, as I said, it's generalization. You just change my AC functional to this PMC functional. You change number C to a function. This is similar to what Professor Gromov used in describing the mu bubbles. The main challenge is to build up this the MiMax theory. Okay. And analogous to Yale's conjecture, we can also conjecture that in our n+1, given a smooth function asymptotic to a constant, there should exist almost embedded hypersurface with prescribed mean curvature h. Or that the mu bubble problem is solved in this case. Oh yeah, so the question generic assumption. Yeah, I mean in my first paper with Zhou, we added a generic assumption here. But I mean we have some unfinished notes. I mean I think we can prove a general h. But for the general h, the description of the limit will be complicated because you may have some minimal pieces. So the description will be a little bit complicated. So thanks for the comment. I'm a little bit rushed, but I still want to use 5 minutes to quickly explain and I think an elegant application of the ideas in studying the volume spectrum initially raised by Professor Gromov. So in 1961, Almgren proved that if you consider all of the separating hypersurfaces, which are surfaces that separate the manifold into two parts, modulo Z2 action identifying the two orientations, you show that the space is weakly homotopic to RP infinity, infinite dimensional real projective space, or you call this mod 2 flat chains. So this topological observation tells us that the Z2 cohomological ring is a polynomial ring with a single generator lambda. So using this structure, we can define the so-called key sweeport. So Liam will going to talk more about the definition. More or less, this is defined as say a key parameter family of hypersurfaces satisfying this topological non-triviality condition. So based on this, Professor Gromov defined this volume spectrum and later by Goose and Marquez Neves. It's mainly a sequence of numbers defined using the MiMax definition applying to key sweepers. So these are key parameter family of hypersurfaces. You take the maximum and you take the infimum. By definition, the sequence of numbers is monotonically non-decreasing and diverge to infinity at this rate. This was also observed by Gromov. We can also adapt the MiMax theorem by Almgren, Peace, Simon to show that each of the number is achieved by integer linear combinations of minimal hypersurfaces. They're smoothly embedded in lower dimensions. Well, an interesting program initiated by Marquez Neves was to approach a conjecture by Yale on the existence of infinite many closed minimal surfaces. So their program was to apply the MiMax theorem to the volume spectrum, Gromov volume spectrum. A key challenge was that in the definition, there are always these integer multiplicities, which means that if I apply the theorem to omega 2, I may get the solution for omega 1 counted with integer multiplicities. If you think about the two-dimensional case, so in the first, for omega 1, you may construct a closed geodesic. For omega 2, you may construct the geodesic running across itself twice. So the presence of integer multiplicities tells us that, well, you cannot easily obtain infinite many solutions by directly combining the two beautiful series. Well, they conjecture that if the Riemannian metric is generic, the integer multiplicity should always be 1, which was proved by myself in 2019. Say, at least for generic metric in the sense of Bayer category, the MiMax theorem applied to the volume spectrum always produce multiplicity 1 minimal hypersurfaces. And later on, Marquez Neves also proved that the Morse index of them are exactly K. So in the last 1 minute, I just want to make a quick connection between the mu bubbles, the PMC hypersurfaces, with this multiplicity 1 conjecture. Indeed, I found that if we perturb the area functional to the AH functional, this functional is defined to be the area minus the integration times an epsilon. If you do these simple perturbations, you can get something magic. The key challenge was that the area functional is defined over the mod 2 hypercycles, while the AH functional is defined on the double cover of the mod 2 flat chains. You have to do a double cover lifting to translate or to interpret the volume spectrum as a local MiMax over this contractible space. Once you were done, you can choose the prescript function in a nicer way, in a nicer manner, so that the multiplicity 1 solution corresponding to this functional can only convert to multiplicity 1 solution for the area functional. So that sort of give the proof. Well, I'm sorry, I maybe overused my time. I'm sorry for the rush in the second part.